Now finally, let's talk how to calculate the confidence intervals. The problem is that median doesn't follow any distribution, so you cannot use parametric approach to calculate confidence interval for the median. Okay, you can make a test using ranks, but you cannot calculate the confidence intervals. What to do in this case? Well, that's the answer. It's a bootstrapping. Okay, what is bootstrapping? Literally speaking, bootstrapping is when you try to lift yourself using the bootstraps, meaning that boots are on you. So of course in real life it's not possible, but that's the only thing you have to lift yourself. Okay, so what to do in this case? Well, in statistics, luckily it's possible, and there is a little trick that allows you to do that, and let's discuss it. Okay, so the idea is to estimate the distribution. So we don't estimate the parameters of the distribution because the theoretical function is not known, but we can estimate the distribution itself. So it means that we can estimate like thousands of points. We can mimic the situation which we discussed several times when you go to a population and take thousands of samples. In reality, it's not possible, but bootstrapping allows you to make a simulation of this process without having access to the population. Okay. And the idea is following. Instead of making inference sample population, you make inference resample sample. Sample is everything you know about the population. It came from the population, and we assume it's at least random and representative. So let's take many subsamples from this sample and use these subsamples as to make a distribution. Okay. So that's the procedure. Use computer to take many means thousands random subsamples of the same size from your sample. Calculate statistic for every subsample and make a distribution. And then if you want to calculate, for example, let's say you take 10,000 subsamples, so you will end up with 10,000 average values, right? And then you take 2.5% smallest out, 2.5% largest out, and that will be your confidence interval. And you can do it with any statistics at all. So you can do it with any statistics. We can calculate correlation 10,000 times. You can calculate median 10,000 times. So it works with any statistics, and it works with any samples. Okay. So once again, sample is the only representation of your population. So we use sample to mimic these many subsamples from the population, calculate statistics for every subsample, and then make a distribution of these statistics. So literally speaking, you can use bootstrapping when you cannot calculate confidence interval because statistics doesn't follow any distribution, right? For example, Spearman correlation coefficient doesn't follow any theoretical distribution. Median doesn't follow any theoretical distribution. You can invent your own statistics, which, for example, you cannot calculate the confidence interval for, but you can do it with bootstrapping. The key idea of bootstrapping is sampling with replacement. What it means? It means you take a subsample from your sample, then you sort of return all the values back and make a new subsample. So in this case, it means that some of the elements of your samples will appear several times. Let me show you an example. So let's see how it works. So that's our sample. Of course, in reality, it should be values. I just make it for the visual purposes. So we have the ranks, or just the order 1, 2, 3, and 4. It's like a vector with 4 values, right? So let's say we would like to generate the first subsample, and we will use die, the D4 for that. So let's say we roll this die. Let's say we have 4 dice. So we roll all of them, and we got 1, 4, 2, and 4. Okay. So that's your first subsample. That's how it will look like. So you can see 1, the sample number 1, the value number 1, the bottle number 1, bottle number 4, bottle number 2, and bottle number 4. Okay. Then let's say you roll die a second time, and you got, for example, 1, 2, 2, 4. Well, that's the second subsample. Then you did it again and got, for example, 3, 2, something very extreme, 3, 3. So that will be your next subsample. And then you just continue 10,000 times, for example, or 5,000 times. The more the better. And then you will calculate for every subsample. You can calculate some statistics. For example, it can be the average alcohol content in this beer, and then make a distribution. So you will have 10,000 values. You can make a histogram, a very nice histogram that will show you the distribution. Then you can use this distribution to calculate confidence intervals. Okay. So that's actually how it works. And of course, you cannot do it manually. In this case, you definitely need to use some programs like R or similar. And I will just discuss it quickly, how to do it in R. And then I will show you all the details in the next video. if you want to do it in R, you have to install a package. That's the package name boot. So you have to use install packages and then find the package boot that contains all functions necessary for bootstrapping. The main function is called also boot. And this function actually does the main job. It takes all the subsamples and calculates the statistics. To do that, you provide 3 arguments. First, it's data. It can be vector, matrix, or data frames. It's up to you. Then the second is a function which will calculate statistics for a subset of your frame, for the subset of your data. So for example, if it's a vector, it's a subset of your values in the vector. If it's data frame, it's a subset of rows in this data frame, and so on. And you have to write this function yourself. I'll show you some examples soon. The third argument is just the number of subsamples, number of iterations. Never do it below 1000. The more the better, but the more the longer time it will take. Okay, usually I use 5-10,000 when I want to do that. Okay. Then this object which boot returns, it contains a lot of things. First of all, the most important, it contains this all the statistics it calculated. For example, in this case, I use 10,000. That means that in object $t, object $t will contain 10,000 values, statistics for every subset. Okay. If you want to calculate confidence intervals, you want to do it yourself, of course, manually, but it's a bit tricky. So you can just use function bootci. It takes several arguments. It's your object from boot. It's a confidence interval, and also type. It has several methods to calculate confidence intervals, but it was proven that BCA is one of the best. Then how to write the function. That's an example of the function, and it's a very simple one which calculates the average value. You can write your own function for median, for any statistics, for standard deviation, right? So that's the name of the function. You can use any name at all. It's up to you. It always has 2 arguments. It should be data and int. Okay. Data is your data, vector or data frame. Int, it's something that boot provides you. Int, it's your subsample. Okay. For example, in previous case, we had a subsample 1, 4, 2, 4. The first value, the fourth, the second, the fourth. That's the int. So it's index of the values or the rows if we are talking about data frame for your subsample. Okay. And then you just take a subsample of your data using int, like I do here. In my case, data is vector, so it's easy. And then you calculate statistics. So in this case, I calculate the mean and return it. Okay. So in the second block, you can see the whole procedure. First of all, I use library boot to get the package to the memory. And then I generate, you see, 5,000 average values. So I use my function boot mean. I generate 5,000 average values using the sample provided as a data. Then I can make a histogram for the calculated average values, or I can calculate the confidence intervals with 95% confidence and show it. Okay. So again, in the video how to do things in R, I will give you a little bit more details and show how to make it. And then to conclude, non-parametric methods, of course, are quite useful, especially if your data doesn't follow any certain distribution, you have outliers or any other problems. They are very simple and intuitive. They are all based on ranks of the values, and it makes the understanding of how to calculate statistics quite easy, from my point of view at least. They are robust to outliers, and one more thing I haven't discussed is that you can use it for discrete data. It's not necessary only having continuous values like we usually, for example, do for t distribution. There are 2 main drawbacks. First of all, they need at least 20 values as a sample size. You can work with a smaller sample, but it will not be very reliable in this case. And then they have power which is smaller than parametric power. We have seen that already when we compared the values with a t-test. You see the t-test always gives you a smaller p-value. And because we know the distribution, we know that it's reliable, right? Non-parametric methods always give you a little bit larger p-value. So it means that if you have a small effect, you will not be able to see it. And that's actually one of the reasons why you need at least 20 values, because you remember that number of values also influence the power of the test. Okay. So that's it. Let's talk about how to do things in R.